Today's topic comes from Simplifying and Solving Equations, Three Types of Solutions. Our essential question today is, what are the three possible types of answers to look for when solving equations? Please take a moment, pausing the video if you need to copy down the topic and essential question into your header, along with today's date, set up your question column and your note column, and resume the video when you're ready to begin. So jumping right in, there are three types of solutions, and the first is one solution. That is what we've seen so far in working with equations where x our variable, or whatever variable we're using. When we get down, we end up with x is equal to some number, a value, and then we are able to plug that answer back in and check our work. So everything we've seen so far in working with equations have been one solution type of equations. So today we're introducing the other two types. You can see them here, infinite solutions. So what happens when you have an infinite solution to your equation is when you can simplify it all the way down, and what you'll end up with is 0 equals 0. The variables will cancel out, the constant terms will cancel out, and so you end up with nothing on either side. We'll look at an example of that and talk about what that actually means to have infinite solutions. You might have some ideas already. And the third type is no solution. So in this one, you'll notice there's also no variable. So the variables cancel out, and what happens when you go to do that third step of moving the constant term is that you end up with a situation where you get two numbers on either side of your equal sign that are in fact not equal. And so when this happens and you get a result like this where you get an equation statement that is not true, it means you have a no solution. So we're going to dive in, look at three examples, one of each type, and explore more about what these different types of solutions mean. Here is our first example. Here's the equation, and we're going to follow the same steps we've been using to solve equations. So looking first to simplify each expression on the left and on the right, and it looks like the right's already simplified, and then to move the variables, then the constants, and isolate the variable. I'm going to invite you to pause the video here if you would like to, and try and use the practice we've been doing in class and in these video lessons to try and solve this equation and see if we come to the same result. So when we simplify each expression, like I said, the right was already simplified, so I just copied that down, but we have the -2 here to distribute, so -2 times x gave me the -2x, -2 times a +10 gave me the -20, and then I just brought down the subtract 3x. But if you notice, there's still a little more work to do to simplify this left side. See if you can spot that, and let's check back in. So if you combined the -2x and the -3x, because they're like terms, I would agree, giving you a -5x and bringing down the -20, subtract 20 as our constant term. So we've finished step one. So far, we've simplified each side of our expression, and we're ready for step 2. This is where we're going to move the variable terms. So we have variables on both sides, in this case -5x and 7x. Which one do you think we're going to move? So I always choose the lowest term with the variable, so -5x was lower than 7x's, so I did the opposite of -5x or -5x and added 5x to both sides. It cancels on the left, and I bring down the -20. On the right hand side, 7x plus the 5x's gave me 12x, and I bring down the +4. So now our equation is a two-step equation, -20 equals 12x plus 4, and we're ready for step 3 to move the constant term. So looking at this, Remember, now we've done our job of getting all the variables to the same side. So now that all of our x's are here, we don't want any constants, so how are we going to move this positive 4? That's right, we're going to subtract 4. We're going to do the opposite. So that cancels out by subtracting 4 there. We bring down the 12x on the right, and we do our calculations on the left. So we had the negative 20, we're subtracting 4, so that brings us to a negative 24 on the left is equal to 12x. So we're ready for step 4, isolating the variable. So in this case, x is being multiplied by 12. What are we going to do to break that apart? If you said divide both sides by 12 because x is being multiplied by 12, I would agree. So what is our final answer if we take negative 24 divided by 12? So we should end up with x is equal to negative 2. So remember, our fifth step is always to check our solution. Let's take a moment off to the side here and do that. So pause the video and see if you can plug negative 2 into the original equation to check to see if that is a solution. So I've gone ahead over here and took the original equation, and everywhere that there was an x, I substituted in a negative 2, since that's what we got for solution over here. And when I simplified the left and the right using order of operations, I got the same answer, negative 10 on both sides. So that, like we can see here, this is an example of one solution, because x is equal to an exact value, negative 2, meaning that the negative 2 is the only value that can be substituted in for the variable, in this case x, like I did here, to make it a true statement, to make sure that when we do that, we get the same thing on both sides. So these are the type of equations we've been working with, where we get a one solution. Let's take a look at another example. So here's our second example. Here's the equation we're going to use. As you pause the video to copy this down, see if you can go ahead and simplify each side of the expression. In this case, both the left and the right need to be simplified. So on the left, I combined negative 6 and a positive 2x, and that combined for negative 4x. Brought down my constant, negative 8. And so this is as simplified as that gets with a variable term and a constant term. On the right-hand side, we have to do this distributive property, so negative 2 times 2x gave me the negative 4x, and negative 2 times a positive 4 gave me the negative 8x. So I just want you to notice something here. Do you notice anything here about our two expressions? Yeah, they're the same on both sides. This should be an indicator that you're going to get a different type of solution than a one solution, because we have the exact same thing on both sides. Let's see what happens when we go ahead and do step 2, moving our variable terms, right? Because what's going to happen? Well, we typically look on both sides and say, let's take the one that's lower and cancel that out, move that one. But in this case, they're exactly the same. So let's just cancel out this negative 4x. What would we have to do? Okay, well, if you said we can add 4x to cancel this negative 4, I'd agree with you, and of course we're going to do that on both sides. So this cancels out here, negative 4x plus 4x, bring down my minus 8 or negative 8, and then the same thing happens on the other side. If I add 4x, it cancels out the negative 4x. So this goes away, and I bring down the negative 8. So now I have the same thing on both sides, and right here is the indicator, but let's go ahead and do one more step to see if you can see what type of solution we're going to get based on what I showed you at the start of this video. Okay, so that step 3 is to move the constant term. So we have negative 8 and negative 8, so we're canceling that out, trying to get those constants together. So since they're the same, what are we going to do to cancel that out? Yeah, we're going to add 8 to both sides, and we get 0 is equal to 0. Well, check back at the top. What type of solution do you think this is? This is an example of infinite solutions, and we can always see that right from the start. When we start to simplify the expression, we should know whether we're going to get a one solution, infinite solutions, or as we'll see in a moment, no solution, because right here when they simplify the expressions and we get the exact same variable term and constant term on either side, the x's are going to cancel out each time and on both sides, and it's going to simplify to 0 equals 0 when you move through to step 3. There's no need to do step 4 to isolate the variable, because by up here when we move the variable terms, they cancel out. So infinite solutions are when you have the same expression on both sides in their simplified form, and when you go to solve it, we get 0 equals 0. So let's take a look at our third and final example and see how that compares for a no solution. So for example number 3, let's go ahead and copy down the equation and do step 1, where we are simplifying each expression. So let's go ahead and simplify each side and take a look at what happens. Okay, so on the left we should have done the distributive property. So we're taking half of each term inside of the parentheses. Half of 10 is 5. Half of negative 14x is negative 7x. On the right, we had to combine like terms. We had x terms to combine. So negative 9x plus 2x is a negative 7x. And then bring down our constant term of positive 3.5. So each side is simplified. What do you notice this time? Is there anything that's the same or different? Well, if you notice, we have a negative 7x on the left, and we have negative 7x on the right. What do you think is going to happen in step 2 when we move the variable terms? Probably a lot like above, because when we go to pick the lowest one, they're exactly the same, so we're just going to add 7x to both sides. As we do that, so we add 7x to both sides, and since it's a negative 7x on each side, the x's cancel out. And now we bring down our constant. So on the left, that's a constant of 5. On the right, that constant is a positive 3.5. So as we go to do step 3 of moving the constant term, we're kind of in a pickle here, but I will just usually choose the lowest one. So I'll continue this through, and let's go ahead and cancel out this constant term here of 3.5. So I subtracted 3.5 from both sides, and it canceled out on the right, so that got me 0. On the left, when I take 5 and I subtract 3.5, I get 1.5. So I end up with this statement that says that 1.5 is equal to 0. Is that a true mathematical statement? No, it's not. So what this is, when that's not true and we've done all of our steps and we checked our work, this is going to be an example of no solution. So in that case, I'll just put a slash through the equal sign, meaning that 1.5 is not equal to 0. That's not a true statement. And what I'll do is I'll label that as a no solution. What this means is that the x cancels out, the variables, in this case x, cancels out, and it simplifies down when you go through steps 1 through 3 to 2 values that aren't actually equal, like we saw here. And so this is just, again, an indicator of when you'll see that. And so you can actually start to tell from step 2, after you've done step 1, that when you've simplified each expression, the variable terms are exactly the same. Like here we saw negative 7x and negative 7x, but the constant terms are different. In this case, we had a 5 on the left and a positive 3.5 on the right. So as you start to move the variables and move the constants, it's up here that you see, oh, those variable terms are going to cancel out. I'm going to end up with 2 numbers that are not equal. So it's right here that you're like, yep, this is a no solution. And you can carry it through down to 0 on one side to prove that. So this is going to conclude our video today, introducing the 3 types of solutions. Please make sure that your notes are complete and come ready to do more work like this in class.